Okay, guys, well, welcome back. We're about to do 2I, so we've just done 2H, and this is about solving inequalities which involve modulus brackets or absolute values of expressions. So there's only a few questions here, and as you can see, that's what we were talking about last time around, they say the absolute value property is very useful in solving modulus inequalities, and they're talking about the properties were given to you earlier on, and they're essentially talking about this. Okay, when we say, remember when we talked about the common ratio being in between -1 and 1, we could say the modulus of those numbers are less than 1. So I guess it's easier thinking about it from this way round to this way round. So if the common ratio, for example, between -1 and 1, when you take the modulus of any of those numbers between -1 and 1, any of those, and say, for example, take the modulus of -0.7, you're going to end up getting 0.7. So all of these will be essentially pushed over here. And so we'll be talking about the modulus being less than 1. Modulus being less than 1 essentially will mean from here to here. Okay, so if you're happy with that, then the other side of this should be fairly obvious as well. If I said, well, no, in fact, the common ratio is actually greater than 1 when I take the absolute value of the common ratio, that is. So that would be to say, well, r could be greater than 1 or r could be less than -1. So on the number line, we're talking about -1 there. So absolute value of, say, -2 over there is going to give you 2, for example, which would be greater than 1. Okay, so if you've got the modulus brackets being greater than something, that's going to split up into two cases. R is greater than 1 and r is less than -1. Okay, right. I mean, that's obviously just the generalized version, but okay, so let's have a look at the questions. We've got example 18. Let's take this one. So it says solve and check your answer graphically. So for the first one here, we're going to say, so this becomes 2x minus 4 is in between -4 and 4. So that's the rule which we're using. Now, normally when we're solving these, well, often we'll try to start off with by just doing the same thing to all three parts. But formally, we should really treat this as two inequalities. We've got this one, and we've got this one over here. Now, often it will be fine just to do the same things to all three parts of this. And I think this is a case where we can do that. But later on, we'll see different cases where we have to split into the two sides. So let's add 4 onto everything to start off with. We'll get 2x is less than 8, and then let's divide by 2. So we get x and is less than 4. So there we go. We have now solved this. Check it graphically. Well, when you're doing this graphically, 2x minus 4, so it's going to cross at -4. It's going to go up in 2, so it's going to cross at 2 there. And so it's going to go like this. There's 4, saying this is going to be less than 4. So get rid of that. Less than 4 is in the region from x is 0 to x is 5. That's 2 up to 4 then. So we're talking about this region here is when this graph is less than 4. Okay, so we are less than 4 between here and here, and that's the domain of x is between 0 and 4. So yes, it's checking when we look at the graph. Okay, now for you, when you're doing these ones, you can do it by plotting this one on your calculator and plotting this on your calculator. So you'll need to come up with two functions, and I think on your calculator it says f1 of x, and if you just use the cursor key, then it will give you in the formula bar a second function which you can type in. So this is one function, and this is another function which you can type in, and you can plot them both on the same graph. You can also find points of intersection if you analyze the graph. So if you go to menu and analyze the graph, it will enable you to find points of intersection. It's pretty straightforward, to be honest. Okay, so let's look at the second part of this question. So second one here, we are talking about doing this the other way around. So we're saying 3 minus 2x has got to be greater than or equal to 1. So that's one of the conditions. And the other condition is going to be 3 minus 2x is going to be less than or equal to minus 1. So those are the two things which are coming out. And remember, if you're struggling a little bit with that, just to remember it, just always go back to that basic example. With r, if it's greater than 1, that means that r is greater than 1 or r is less than minus 1. So this turns into those two inequalities. Okay. Right, so let's deal with this by perhaps taking the 3 to the other side. Okay, so we get minus 2 there. And then remember, with inequalities, if you divide by minus 2, you'll need to change the sign around. So there we go. We're going to get x is less than or equal to 1. We could have avoided that, by the way, by taking the minus 2x to the other side, and we would have got 3 is greater than or equal to 1 plus 2x. And now take away the 1. We've got 2 is greater than or equal to 2x. Now divide by 2. We're getting x is less than or equal to 1, or 1 is greater than or equal to x, which is the same as this thing here. So we can avoid dividing or timesing by a negative and switching the sign around by just moving the negative term to the other side before we divide. Okay, same. Let's just get rid of that. So likewise with this one here, we can take the 3 to the other side, getting a minus 4, and then dividing by minus 2 gives us 2 there, and then we'll need to change the sign around. So we're getting two solutions there. We're getting x is less than or equal to 1, and we're getting x is greater than or equal to 2. Now, graphically, let's just try and put this over here. We've got 3x minus 2. So crossing at 3, gradient of 2 should cross at 1.5 with gradient of 2. And then that's going to flick up the other side, so we can get rid of that bit at the bottom. And so if we want to know when is this greater than or equal to 1, so we can put now a height of 1 on. So there's 1. And where is it greater? It's greater here and here. Now that means the x domain for which it's going to be valid is here and here. Now I'm assuming that this point here is 1. Yeah, it should be 1 because we have, a little tricky to see here, 1 across and 2 down. We have a steepness of 2 there. So so this point should be at 1, and this point here should be at 0.5 past 1.5. So that should be at 2, which is exactly what we've got. We're talking about x is being less than or equal to 1 and greater than or equal to 2. Okay, you can obviously check that one on your calculator, but I expect at this point you're able to check that by sketching the situation as well. Okay, so next one, we've got example 19 here. So solve x squared minus 5x is less than 6. Now for this one, then we can set this up by saying x squared minus 5x is less than 6, but is greater than minus 6. Now, this is where instead of doing the same thing to all three parts, we're going to need to split it up into two inequalities. And that is really formally what we should be doing every time anyway. It's just that sometimes we get away with doing the same thing to all three parts. Now, if I was going to try and do this same thing to all three parts, I'd need to complete the square here to get x on its own. How do I complete the square with those two sides? So you can see obviously that we're going to need to split this one up. Okay, so we've got x squared minus 5x less than 6 here. So bring everything to one side. Preferably make x squared positive, just makes the factorization easier. Okay, and there we go. So we've got x is what is that, -3 and, oh no, it's not, it's -6 and +1. Okay, so the two numbers that work there, two numbers which add together to give -6 and add together to give -5. And then on the other side, we've got x squared minus 5x plus 6, and I'm expecting those brackets to be, let's see, so we're getting, oh, so this one's slightly different. We're getting a 3 and a 2 inside the bracket. So -3 plus -2 gives us -5, but they times together to give +6. So different numbers inside the brackets there. Okay, and now we need to solve these. Now, you should have done this in previous courses. So, for example, if we're going to solve this, we could perhaps do a little sketch of this and say, well, okay, we're going to have roots at 6, and we're going to have a root -1. This is a positive quadratic. If we plotted this, if we called that y, and we're saying, well, when is that less than 0? Well, it's less than 0 in this region here. So we can then say that our solutions are between, x is between -1 and 6. And then if we look at this one here, so for this one we can say, similarly, have solutions of 2 and 3. Again, it's a positive quadratic, and we're looking in this case, where is this positive quadratic greater than 0? We're talking about this part, and we're talking about this part here. So this one is going to give us two solutions. It's going to be when x is greater than, sorry, when x is less than 2, and when x is greater than 3. Okay, so now we have a bit of a problem here because we have two sets of solutions. We've got this set and we've got this set, and somehow we need to combine them. But this isn't saying either this or this. It's saying that both of these conditions have to be true at the same time. So the solutions here have to match up with the solutions here. So we need to find out which of these solutions match up with these solutions here. So we can't just say either this or this, because that's not what the question is saying. It's saying this and this. Okay, so let me just get rid of everything for a moment. You can obviously just pop backwards, but let's just get rid of that. And I'm just going to do a number line again, and then I'm going to show this graphically too. So we've got between -1 and 6 was valid. That was one of our sets of solutions. So open circle at the end of each of those. And then we had 2 and 3 here. So we have less than that is valid and greater than that is valid as well. Now, where are those things concurrently true? Where are they true at the same time? Well, between here and here they're true, and between here and here they're true. So between there and between there, they're both true. Okay, that's where they overlap. So because we're saying that both the left-hand side of the inequality and the right-hand side inequality have to be true, then we have to overlap these two things. It doesn't say or, it says and. Okay, so well, when is that true? We've got between -1 and 2. We could say that for x. And on the other side, we've got between 3 and 6. And there's no equals because there was no equals in this case as well. So that's the final set of solutions. Okay, well, just to go back and check this whole thing graphically to see what's happening here. This on the left-hand side could be factorized as x and x minus 5 less than 6. Now, if we were going to graph x times by x minus 5, then that would give us our roots of 0 and 5. This would be a positive quadratic, but this part of the quadratic would be reflected upwards because we're taking the modulus of this. So let's just try and put that in as best as I can. We've got something like this and something like this, and it goes up like this. Okay, now the problem with me graphing this is I don't really know where the height of 6 is. So the height of 6 could be up here, or the height of 6 could be down there. However, I actually know where it crosses here, and I know it does cross here, because we can see that there is this kind of empty gap in the middle between 2 and 3. And so between 2 and 3, right, so that's what we've got there. Between 2 and 3, this should have gone up a bit like that, okay? But we should have a point there and a point there which is above 6 and not below 6. My graph is a bit rubbish. There we go. So this is our height of 6, and this graph here is beneath 6, between here and here, and between here and here. Now you can practice with your GDC, and you can check where the intersections are. You should find out that the intersections are at 2 and 3, and I don't know, maybe the whole numbers on this side and this side, or maybe they're not. Okay, so what am I talking about? Of course I know. They're -1 and 6. Oh, okay. So let's have a look at this. Yeah, they're saying confirm graphically here as well. Okay, right, example 20, and example 20 is going to be super quick, because example 20 is simply saying, just take this one here in case I need to write over it. So this one is simply saying solve this thing here graphically. So graphically, as they're saying here, come up with your first function and then your second function, do this on your calculator, and then find out where these two things are intersecting. You should get two graphs like this, and on your calculator, when you go to analyze the graphs, you can find the points of intersection, and it will allow you to do them one at a time, I believe, and you then basically have to define the domain in which you're looking for a solution. So if you come up with your domain lines between like here and here, so don't go until you hit that asymptote, then you should find this solution here. And you can do the same thing again to find the other point of intersection. Now, in terms of where is this less than 1, well, we can see it's less than the line of 1 when it's underneath the line of 1. So we're going to say whatever this point is, we're going to say, well, it's beneath this point. So x values are less than the x value in that point, and x values are greater than the x value in this point. Greater than 1, less than 0. Okay, that one's actually dead simple and an easy way to end. Okay, so let's look at the exercise briefly. And, reflect, how would you solve example 20 algebraically? Well, I'm not going to do that myself just at the moment, but I'll let you have a think about that one, of course. And there's exercise 2I, so you can have a go at that. And next we're dealing with piecewise functions. So see you for the next one.